Welcome to Lab 3, Part 2. In this lab, we're going to be exploring Landfire data and recording possible errors in the Landfire data that we'll correct in a future lab. Landfire data has become the backbone of many landscape-scale fire management projects. It serves as the basis for fire behavior runs and as a tool for communicating current and future vegetation characteristics to validate and justify field treatments. Landfire usually requires calibration. Sometimes substantial changes are required to increase the accuracy of its application. More informed and accurate fire and fuel modeling lead to more confident decision-making and resource allocation. There's a need for more areas around the country to maintain updated Landfire layers and contribute to the overall quality of the product for all users. The accuracy of Landfire varies depending on where you are and how you plan on using the data. Most of Landfire data would be considered very accurate. Some might just be a little off, and some might be really off. It's therefore very important to calibrate the Landfire product to catch the data that's really off, and some of the data that's a little off. As shown by Helmbrecht and Blankenship in 2016, fully calibrating Landfire can be an enormous effort, and one carried out by those very familiar with the area. Without that kind of time or familiarity, we will do what we can with what we have, and also take some input from local resources. GIS and fire management is often a balance of what should be done and what you have time to do. Sometimes you have to make sacrifices in what should be done to get something produced when needed. In addition to the importance of calibrating Landfire data and correcting errors, the process of going through the data is very informative and will lead you through the important decision-making processes that will help you get more familiar with your area as you move forward with fire modeling. In the document, How to Prepare Landfire Data, steps for validating Landfire data have been summarized from Stratton and Helmbrecht and Blankenship. These steps are just a suggested starting place to think through your data, but completing these steps with some attention to detail will reveal important information about the accuracy of your data product. The environmental assessment for the BBB area accomplishes the first step of defining objectives. The purposes of the project can be summarized as 1. Reduce wildfire risk, especially in the wildland-urban interface, and 2. Reduce the area to a more historic fire return interval. For this class, we'll be focusing our assessment on wildfire risk reduction. You have also accomplished the second step of downloading Landfire data with the proper projection. An indication that you have not downloaded the data in the proper projection is that your Landfire data is skewed. If that is the case, you will need to re-download the data or contact Heather Heward for assistance. In the following steps, you'll be exploring each layer and some combinations of layers and record potential changes that will need to be made before using the Landfire product. The quiz questions will prompt you to think about how the layers should be changed, but you should also start to populate the table below as a summary of potential changes needed to the Landfire layers. Before you begin, go to your Lesson 3 folder and create an Outputs folder. Once created, you can go to Geoprocessing, Environments, and set up your workspace to the Lesson 3 Outputs folder. You will also need to open the How to Process Landfire Data document, as most of the specific details for how to perform these processes are in this document. We are here on Step 3, which is comparing our project location to Landfire data map zones. If you have LFDAT, you can turn on the Add CONUS layer and also turn on some Landfire data from your project. And we'll drag this down, not in the Landfire folder. Minimize those and zoom out. If you don't have LFDAT, you can simply observe where the project is in my project here. So what we're looking for is if our project crosses the boundary of a Landfire zone, and it does not, and it looks like it's not too close to the boundary where we might expect some impact of these different rule sets that are applied to each of these zones. So for each of these zones, The Landfire team collaborated with experts in that region to determine how best to interpret the Landsat imagery and relate that to these landscape layers. And so if your project is on a boundary, you might see some distinct changes from one zone to the next. Our project does not appear to be impacted by that. Step 4 is updating for disturbances. Since 2012, when the Landfire data was collected, there have not been any significant natural or man-made disturbances in this area, so we can move on to our next step. If you did have disturbances in your area, then as discussed here, you would want to make sure you had the polygons for each of those disturbances and understand how that disturbance impacted the different layers in Landfire. Step 5 is to familiarize yourself with the definitions and units for each of the layers. You can see the Landfire Data Dictionary for full descriptions of each of these layers. And we can also, as a quick reference, look at the range of distributions in the table that's provided. We're going to start our analysis of each layer by zooming back in and expanding the Landfire. Beginning with the FBFM 40, we're going to right-click and open the attributes table and select Create a Graph. For the value field, we will have that as count, and the X field label will be FBFM 40. And it's best to expand this and answer the question about what the 5 most prominent fuel models are. The interpretation of these fuel models and whether these fuel model selections are valid comes through talking with someone that has experience in both the fuels and how those fuels behave. To get at that information a little bit, we do have some photos that we can look at in our BBB data folder, and also we have an Excel spreadsheet that's available on BBLearn called Compare Models 4. So in a conversation that I had with Dustin Doan about the fuel and fire behavior in this area, we looked at this high occurring GS2, and we looked at some photos of the area and a grass shrub 2, knowing that it's expected to behave with significant rates of spread under high winds and also flame lengths that are pretty high, even in moderate to moderate winds. And his experience showed that these areas don't burn with that kind of fire behavior. These low shrubs and minimal grasses have a lot less fire behavior than these grass shrub and grass fuel models. So we explored various different fuel models to see if we could find a better fit. And one that we looked at was this TU2, a timber understory 2. So for flame length, he felt that this flame length was appropriate for what's been observed in the area, and rate of spread was also more reasonable for what they observed. This is going to make a big impact across the landscape if we are going to apply a broad scale change to change all these GS2s into TU2. So right now TU2 is very underrepresented, but he believes that that's a better representation. And if you want to get a better idea of what fuel model that is, you can look up the GTR 153 and see more of a description of each of these fuel models. So the name of TU2 is Moderate Load Humid Climate Timber Shrub. Well, this is certainly not a humid climate, but one thing that I've been learning about fuel models is that pictures and even the names shouldn't dissuade you from using that fuel model if the fire behavior is appropriate for your area. So we will continue on with using the TU2 fuel model as a recommendation when we make this change in the future. Next, we'll be looking at elevation. Here are where our mountain peaks are going to come in. I'm going to turn on my mountain peaks, and I'm going to use this selection feature, and I'm just going to draw a box around my project area. and that's going to select all the peaks that are in this area. And I'll right click and selection, create layer from selected features. And I will just remove this one here, don't need that. And referring to my how-to document, we're going to be using the tool extract values to points. I'm going to go to my search function and search for extract values to points. My input points selection, input raster is the DEM, and I will name my output peaks and then DEM. Now that completed really quickly, and it also didn't populate anything in my table of contents, which means that it actually didn't run. So if I go to add here, my outputs folder, I'm not seeing that layer I just created, so I'm going to shut down Arc, save and shut down and start again. So I've restarted and I'm going to try that process again. This time I'm just going to leave it as the default name. So now you can see I have, this is taking a little bit longer, and it looks like I have that process bar there, and it did work. So now I'm going to open this attributes table, and we have a comparison of the elevation in meters from these mountain peaks to the raster values. And you're looking for how different these numbers are, and that'll give you an indication of the accuracy of the Landfire elevation layer. Because I'm finished with that analysis, I'm going to go ahead and remove this, and again keep trying to keep my project as clean as possible. So now I'm going to be looking at slope. Turn off elevation, turn on slope, and opening the attribute table. And we're looking for how reasonable the values are here. So when referencing the degrees of slope, so notice that the units here are in degrees. Often when we're talking about slope in the field, we refer to it as percent. So this is just a breakdown of what that percent looks like. So for example, a 60-degree slope is 173%. And looking at this figure here, it just shows you in reference to what more people might be familiar with, which is these ski runs, steepness of ski runs. So when we're looking at our attributes table, we see that we do have values that are relatively high. So what we're going to look at here is, first of all, are the values reasonable? Are there values over 90 degrees? And we don't have that. We do have several areas that are very steep. So I might just highlight some of these areas that are over 100% slope there. So anything that's over 45. And just see if that correlates with areas on the ground that, at least from my perspective, from this aerial perspective, looks steep, or if I were really familiar with the area on areas that I knew were that steep. So I'm going to turn off this CONUS map layer. I'm actually going to remove this. And I'm going to turn on a base map. So you can see that there are relatively few areas with those steep slopes, but I'll zoom into some of them. And turn this on and off, and it looks like indeed it is corresponding with areas, at least from this view, that do look very steep. So I'm pretty happy with the slope layer. So if I were filling out that table, I would make indications in the elevation and the slope layer, or the elevation and slope are acceptable. So now we're going to look at canopy cover. Open the attributes table. One thing that Stratton mentions is that canopy cover greater than 70% is not as common as is often understood, or as is often thought. So we're curious about how much of our area is in this greater than 70% category. And we need to either become familiar with some of these areas personally, or we'll need to talk to a manager that has experienced the cover in these areas and get their thoughts to make sure it matches. So I'm going to turn this layer on, zoom to layer, which will zoom me out, and explore some of these denser areas. So again, looking at number here, this isn't going to affect a huge area, but if we think about what the application of the canopy cover is, if you have really dense canopy covers, it's going to have an impact on the expected fuel moisture under the canopy, so it might decrease your fire behavior underneath that canopy, and it also might increase the likelihood of active crown fire between trees in your model predictions. So when we're looking at this, again, we're going to turn it on and turn it off. So these areas do look pretty thick. And in talking to the manager, Justin Doan, he believes that these areas, because they have been fire excluded for so long, do indeed have very thick canopies, and his recommendation would be to keep the canopy covers as they are at these higher cover classes. With each of these canopy layers that we're going to be looking at, the changes that we might make in them may come about when we do our fire behavior modeling and we see that we are seeing more active crown fire than we would expect or has occurred in the area. And then at that point we might go back and adjust some of these canopy values so that we can get better correlation with what previous fire activity has been. For our canopy height and canopy base height, this step is mostly just observing the attributes tables and making sure the values are reasonable, but we will get into that in a little bit more detail in a following step. So we'll move on for now. So step 6 is confirming non-burnable areas. In our fire behavior fuel models, there are fuel models that are listed as non-burnable. And in order to really get a picture of what those non-burnable areas look like compared to the ground, it's going to be easier to extract those. To start this process, we'll want to open the attributes table and take a look at these values. So we want to extract these non-burnables. And we're going to be setting up a query statement and pulling these non-burnables out, but it's difficult to pull out these values that have letters in them instead of numbers. So we are going to look for which columns have distinct numbers. We could either make a column that has the number 1 and everything has 0, but these are also going to be sufficient here. So we could say values less than or equal to 99 are going to be non-burnable, or we could even do the row ID less than or equal to 4. So we just are going to note that in our attributes table. And now we will refer back to our how-to guide. And we're going to be extracting by attributes. So you can either navigate to that in the Spatial Analyst tools, or you can just search for it here. Our input raster is going to be FBFM40, and this is a where clause. This is going to say in the value column, anything that is less than or equal to 99, I want to have pulled out. And I'm going to name this BBB non-burnable. I've done this a couple times, so I'm going to name mine 2. So now all my non-burnables are pulled out. I'm going to turn my fire behavior fuel model 40 out. I'm going to zoom to layer, and I can see the various classes of non-burnables across the landscape. So now comes my exploration. I want to make sure that the places that are labeled as non-burnable are indeed non-burnable, and if there are other places at least that look like they wouldn't burn, what they are classified as. Zoom in over here. And you can zoom in wherever you see non-burnable cells and do an exploration all over this landscape. So as I turn this on and off, it does look like there might be some areas that have vegetation that are labeled as non-burnable. Some over here. Might zoom in a little closer there. Looks like that might just be the shadow. So what we're trying to achieve or prevent here is, if we were to run fire behavior across this landscape, a non-burnable cell would not allow fire to pass through it. So if we have too many areas labeled as non-burnable, then it might give us a false sense of fire spread or fire activity. So if we are feeling comfortable with the areas that have been classified as non-burnable, then we need to explore some of these areas that look relatively non-burnable but are not classified as such. So I'm going to turn on the Fuel Model 40 again, and using the Identify tool, I might see which fuel models are in these areas. It's looking like it's a 102. If I expand this out, 102 is a GR2, but we can change the way that that displays. GR2 is that 102 there. And zooming around another fuel model, let's see, let's turn this off again. Another fuel model that might fit into that classification of looking non-burnable but not being classified as this color here. It looks like maybe SH2. So in order to kind of confirm what I am feeling here, I might zoom around a little bit more to different mountain peaks and see if that same pattern exists. And if I'm finding that there is a distinct pattern in fuel models that look non-burnable but are classified as a burnable shrub or a burnable fuel model, then I might need to either consider changing them to non-burnable, but that would have pretty far-reaching ramifications in that it would mean that no fire could ever carry through there even if it got really dry. Or I might figure out if those fuel models are what is going to really represent that area. So I'll go to Extract by Attributes and FBFM 40. And this time SQL statement's going to be FBFM is equal to, and I'll double click the GR2. And change this name to GR2, and this is, I've made this once before already. So here's our GR2 layer. So with this extracted, now we can zoom around to different places around our landscape and see if there is a pattern with GR2 showing up as areas that are pretty non-burnable. When you're doing this exploration, it's important to do it at higher elevations and lower elevations. If you are going to recommend a change, you might not want to change GR2 across the board. It might be something that you only see this pattern in higher elevation places. So you'll do that same process with any other fuel model you feel like might be misclassified across your landscape, just to get a good view of it. If you feel like you're more comfortable in zooming around in Google Earth, then you can export this as a KML file. Just remember that when this exports as a KML file, these squares, these pixels become kind of more fuzzier blobs, since the exact location is a little bit less defined than a polygon. But it might help you look at the landscape a little bit more. Just to keep your scale in mind, this isn't a pixel by pixel analysis. We're looking for kind of an overall pattern. Landfire is a large scale product, and if we feel like across the landscape there's general changes, then we can do that, but don't worry too much about whether or not 1 or 2 pixels is in the wrong place. We're looking for just overall patterns here. So take about 15 minutes to explore the area and looking at the non-burnables first, and then exploring the fuel models around those non-burnable areas, and see if you can identify some patterns. Don't take too much time. You could really spend an enormous amount of time doing this, and really a lot of these processes that we'll do in this lab. The idea here is that you just become familiar with the data itself and also the process of exploring the non-burnable areas. After this exploration, you should be able to answer question 8, which is to list 1 or 2 changes that you might recommend based on your exploration of the non-burnable areas. So now moving on to step 7, combining layers. So going back to my how-to document. Combining layers. We're going to be combining 3 layers just to see how these relate to each other. And what we'll see is we'll start to see some patterns in the fuel models that we might suspect as needing to be changed. So we are going to look at a combination of EVT, so existing vegetation type, canopy cover, and fire behavior fuel model. So we're going to have to do a couple of different steps to get this just the way we want it so that we can have the right kind of table. We're going to go to the combine feature. So I'm going to search here. And combine Spatial Analyst. And I'm going to select my 3 rasters, FBFM40, EVT, and canopy cover. If we were going to do a full analysis here, we might select several other different combinations, but this will work for us for now. And I'll label mine canopy cover, EVT, and FBFM 40. So here's our new output of combined. This one did throw several errors at me initially, and I did have to restart my computer in order for this to work. Just to give you some perspective on how these things go, when you do have an error, and some of you have picked up on this, when you do have an error, you can go into the results category and find what number your error message is. Sometimes you can search the error message and get some answers as to why you would receive that. I didn't find anything helpful in these error messages. I ended up sending it to the person that helps with my GIS problems, and he ran it no problem, of course, and sent it back to me. I ran it again and it worked. So sometimes these things, it's hard to predict why they do or don't work, but if you try it several times after restarting and are not able to get this to create, then please let me know and I will send you a file, and then you can continue on with the lab. So in the attributes table, you'll see that we have a column for each of the layers that's been combined, but it's not the most informative column. And so what we need to do now is join some additional columns here so that we can have the names of the FBFM40, the names of EVTs, and the percentages for canopy cover. So going back to our directions, we are going to be joining fields now. So in our search bar, search for join field, join field tool. So from the input table, we will select our new layer. And we'll say that we want to join the FBFM40 column to the FBFM40 layer. So it's going to say for this layer, or for this column in here, we want to join to this field, and we want our output join field to be value, since that's what both FBFM40 have a value that's the same as this new combined one. So this is the field that they both share, and we want to additionally add FBFM40. So that will say basing off of the value column, we want to also add a column for FBFM40. And click OK. So now our attributes table has a column for FBFM40. And we'll do the same process for the other two columns. Select this combined layer as an input. Join field, this time will be EVT. Join table will be to the EVT layer, and join field is again value. This time it's a little harder to decide what layer to choose from. There's a lot of different EVT classes. So we're going to be choosing the EVT subclass. You can explore, not fuel, subclass. You can explore the different columns and their meanings in the landfire.gov. And so click OK. And now we have our EVT subclass associated. And finally, we'll do our canopy cover. Join field to canopy cover. Join table to the canopy cover layer, and value is going to be the similar one, and this time we're going to canopy cover %, and click OK. So now we have the information in here that we want, but we have some information that we don't want, or that's not useful for us in our next steps. So these three columns, we don't want to get rid of them since they still hold value, but we do want to remove them from visibility, so we can right click and select turn field off for each of those. And if I want to turn them back on, I can go to the table options and select turn all fields on, and it'll expand those out again. The first step we'll be taking to look through this data is to sort by count. We're going to try and figure out the values that have the highest numbers, or the combinations that have the highest number of cells are certainly the ones that will have the most impact across the landscape. So in order to keep track of the cells that I was concerned about, or the combinations I was concerned about, I created a new column here for potential errors. So in here, the table options, you can select add field, and when you are in editor mode, using the editor toolbar, you can edit these values. An editor toolbar can be turned on in your customized toolbars and selecting editor. So walk through the first 10 to 15 or more, if you wish, rows here, and just think about what these, how these three things combined. So this is, canopy cover says this is moderate, has moderate canopy cover, that it's a grass fuel model, and that it's a closed canopy tree. So this all of a sudden has, one, it has a lot of cells, and it has a little bit of information that contradicts. And so I'm a little concerned about this where it says there might be a lot of trees, but it's also a grass fuel model. And what as I might look around, do my same comparison that I did visually with the non-burnable areas, let's just go ahead and highlight these cells and look at our fuel model layer specifically. Hold down Control, take all these layers off, turn Landfire on and zoom out. Oops. I need to turn this one on. So turn my combined layers on, and now I'll turn my base map on as well. So I could pull this out again the same way I did with the non-burnables and get a closer look, but I might just zoom into a section here just to get a general feel. So from this image, do I feel that these might be grass fuel models? Would they behave like a grass fuel model, burning quickly? So that's an area that's a little bit concerning to me. So I'll turn attributes table on again. So I gave that a potential error of 2. So if it were a 1, I would be kind of worried about it. 0 is not concerned about it at all. That's just some way that you can use to keep track of which cells might be off. So non-forested, shrub, deciduous, that seems fine. Non-forested, grass, perennial grass. Both of these seem really appropriate with the way that they're combined. TL3, evergreen closed canopy. So again, not showing a whole lot of canopy closure, and it is showing closed canopy, but this is a TL, a timber litter fuel model, and that seems appropriate. So going down through these more prominent ones, they seem to match up okay. And getting down here, we have a grass open canopy tree. So this is a grass fuel model again with open canopy, so that one might be a little questionable. And then down here we have a closed canopy tree again with a grass. So the ones that were the most suspicious to me were the combinations of closed canopies and grass fuel models. So going through just the most prevalent ones to begin with and identifying which ones were troublesome. We're going to move on and sort for each of these columns and just take a closer look so that we can see if there are other areas that we need to address. So now I'm going to sort my canopy cover. So the things I'm looking for here are areas that have a low canopy cover but are classified as closed canopy tree or closed tree canopy. And what I'm probably going to find is some of this is these errors are compounding, so I may see errors in one place that I also saw in another. So identifying those places, and at this point now I'm looking at their count as well. So this doesn't seem great that it's got open canopy and evergreen closed canopy and grass fuel model, but there also aren't very many cells that are in that category. Now if your attributes table as far as numbers looks a little different than mine, that's fine. We're just going through and we're doing that general analysis. Mine has an additional column that might be separating out my values a little differently than yours. So we'll do the same thing with FBFM40, just sort according to name, and also looking for those combinations that are questionable. So with GRs, are there any GRs that are considered open tree canopy? So here's one, but it's only one cell, so I'm not even going to bother flagging it. And then going down, again, paying most attention to those combinations that have a high number of values in them. In this exploration of canopy cover, it might also be a good opportunity to explore some of the values that were questionable before. If you have these higher cover values, but they're also classed out as evergreen open tree canopy, then those might be ones that we suspect a little bit more as being inaccurate. So perhaps highlighting some of these open tree canopy layers, there might be several of them in different combinations, and zooming around and seeing if there are any concerns with the canopy cover in those specific areas. And also, of course, paying attention to those numbers of cells. If there aren't a lot of cells that are affected by that, then it might not be worth the trouble to go and change them. They're not going to have a big enough impact across the landscape. But it is good to understand what kind of potential errors you have in your data. Now we're going to move on then to the next step, step 8, which is comparing measured stand values. In this area, there was some work done to collect stand information, and we have access to that. In this BBB macro plots, we have information about canopy height, canopy base height, and trees per acre. So to begin, it is going to be useful to look at some of the photos that are available in the data folder. So navigate to your lesson 3, and in your data that you downloaded from BBLearn, there's a folder for photos. And just take a second to, when you start to look at each of these points, you can zoom into the picture and get your own idea of what that area looks like. This is not a picture of the macro plots, but it is a picture of the higher elevation landscape in those areas that we were considering classifying them as something other than the grass shrub that they were. This is what that area looks like, so what that actually might burn like. So we're going to select Extract Multi-Rasters to Points. Our point feature is going to be our BBB macro plots, and our input rasters are going to be canopy height, canopy base height, and we'll also go with canopy cover just because we might be able to think about how the canopy cover is in relation to the trees per acre. And we will select OK. And if we open up our macro plots attributes table, now we have values for each of those columns in our macro plots. Interpreting these data is a little bit more challenging because of the units that they're in. So let's take a second to look at, we'll start with our canopy height layer. If we go to canopy height, we can see that we have a value column, and a value of 25 means that the canopy height is somewhere between 0 and 50 meters times 10. If we were looking to relate this value of 25, 25 would be divided by 10, 2.5 meters. Now our measurements for our plots are in feet, so we would need to first convert to meters and then convert to feet. But the point of looking here is that this isn't just a height of 25, it is this range. So we need to remember that we have a lot of variability in each of these numbers, but we're looking for general trends, and if we feel like the trends that we're seeing match those that were measured on the macro plots. Since it's easier to compare without having to do a little extra mind math, we're going to add some additional columns here. Add a field, we'll label this first canopy height, and L for Landfire, and feet. And this is going to have decimal places in it, so we want it to have, we want it to be a double. And we'll leave those the same for now. Click OK. And we're going to use the field calculator to use canopy height, and it's going to take that value. First we need to divide it by 10, since it's meters times 10, so we have to get it back to meters, we need to divide by 10, and then we need to multiply our meters times 0.23. That will convert it to feet. So now we have canopy height in feet. We'll do the same thing for our canopy base height. Changing to double. And this time, instead of canopy height, we're doing canopy base height, the same calculation. And canopy cover we can keep as %. But again, remember each of these is a range and a pretty broad range at that. So I'm going to expand this out a little bit. So what we're looking for is a comparison of these values. We have canopy height measured and canopy height from Landfire, and looking to see how this compares in each of those points. It's important when you're looking at this information that you understand the large amount of potential error in all the variables that we're looking at. We're just hoping to see some kind of a pattern. There certainly could be some errors in the data that was collected. There might be location errors with the point that where these landed, but we're hoping we do see a little bit of a pattern across areas that have higher canopy heights and areas that have higher canopy heights from Landfire. If we don't see that correlation, then we just might know that our canopy heights aren't super accurate from Landfire in this area, and that's information that we'll have. We might not go and change those canopy heights since we don't have very many points, but we do know how best to interpret our information at least. So canopy height looks like it is pretty across the board, whether it's higher or lower. Now canopy base height is a little trickier. If you're looking at our canopy base heights here, we have 7 and 4, and compared to a 24 and a 13. What we don't know about our data is whether this canopy base height measurement from the field was measured as a height to live crown, and that there is some discrepancies in how to define canopy base height. And you can read about that in this how-to document, that canopy base height is something that's very tricky to measure in the field, and we don't know a lot about how this was measured in our specific incidents. So it's important to understand that maybe our canopy base heights they do feel a little bit low for this area, especially looking at some of these pictures, but what we will base our information on is how they behave. If we get to the fire behavior modeling section and our landscape is transitioning to crown fire way faster than local resources would expect, then we might want to do some manipulation to our crown base heights and our canopy heights. But for now, we'll just make note of the potential differences from measured to Landfire. We have now completed the comparison of the inputs. Our next lab will focus on comparing some of the outputs that this Landfire data will produce and trying to get an idea about how accurate the outputs can be, and making some changes across the landscape and seeing how those changes impact the quality of the outputs. The final step we need to perform in this lab to prepare for next week's lesson and lab is to download ArcFuels. ArcFuels is simply an add-in in Arc, and you don't need administrative privileges to use it. And it provides several pretty useful tools, especially for going back and forth between Arc and different fire modeling programs. To download the add-in, you're going to go to the main page here, and you can, from the left menu bar, you can select Download ArcFuels 10. And you're going to choose for ArcGIS installed on your computer. If you are using Citrix, then of course you can download the Citrix version. So you're going to be downloading ArcFuels, and you'll also be downloading FlamMap 5. Both of them are free programs, so ArcFuels will just install to your computer. You'll follow these directions on how to install that. And for FlamMap 5, this has a link to the site where it's available. Scroll down and select FlamMap software. And installation for either a 32-bit or a 64-bit machine. It's important to read through these notes. They do have special tips on how to successfully download this information. Access to these two programs is going to be useful for the next several labs. You are going to be producing output. If there are significant restrictions or limitations in your ability to download this information or these files or to run them, we can work through that in the following lab. Once you have ArcFuels downloaded, you want to navigate to where the add-in file is located and double-click on it and install the add-in. From Arc, then you'll go to Customize, Add-in Manager, and you should see ArcFuels here. And close. And then in Customize Toolbars, you should see the ArcFuels toolbar. You'll be able to turn that on. And the ArcFuels toolbar is... And that brings us to the end of Lab 3, Part 2. At this point, you should have a pretty good understanding of how the fuel and vegetation layers compare to the Landfire data, and have developed a list of potential changes that should take place to that Landfire data. In the next lab, we'll be producing some fire behavior output and comparing that to what was observed for fire behavior and fire effects on the rapid fire. And then we will make some landscape scale adjustments to the Landfire layers, and then we will compare fire behavior from the adjusted Landfire data layers to the non-adjusted data layers and see if we were able to improve the fire behavior predictions for this area.